You open an app, drop a pin, and request a ride. Behind the scenes, the server has to find every available driver within a strict 2-kilometer radius of your exact coordinate. The simplest way to solve this is to take your coordinate and calculate the exact mathematical distance between it and every single driver currently logged into the city's network. But this is an O of n operation. If there are 100,000 active drivers, the server has to run 100,000 complex distance equations. For a real-time application processing millions of requests a minute, that compute load is impossibly slow. The root of the problem is that traditional relational databases were built to act as linear ledgers. They excel at sorting one-dimensional financial logs or alphabetized customer names, but they struggle to process two-dimensional physical space. Looking at a map, physical proximity is obvious to the human eye. But to query a raw data ledger, the computer only sees distinct rows of numbers without any physical context. Translating physical proximity into a scalable, sub-second backend architecture requires abandoning standard ledger principles completely and adopting an entirely different mathematical model. Standard relational databases rely on an indexing structure called the B-tree. It is highly efficient at sorting one-dimensional alphanumeric data sequentially, like finding a specific employee ID out of a million records. Tracking physical geography, however, means sorting at least two distinct variables, latitude and longitude, at the exact same time. When a standard B-tree encounters a two-dimensional plane, the mathematical logic breaks down. Attempting to index both axes concurrently forces the tree structure to wildly branch and fail. Without a valid index, it defaults to a cataclysmic full-table scan, checking every single row. To query physical space efficiently, back-end systems use spatial databases. These are specialized engines optimized to store geometric shapes and process multidimensional proximity. A spatial database mathematically models the rules of physical geography directly in the engine, allowing systems to natively compute spatial relationships. Before any indexing can occur, the database has to translate physical reality into a queryable spatial format. It does this primarily through the vector data model, representing discrete real-world features using precise mathematical geometries. The foundation of this model starts on a flat Cartesian plane. The simplest geometry is the point, a single coordinate pair representing a specific zero-dimensional location, like a fire hydrant or a parked car. Connecting a series of points creates a line string. This represents one-dimensional paths such as roads, rivers, or transit routes. Enclosing those lines forms a polygon, establishing a solid boundary for two-dimensional regions, like city limits or public parks. While the vector model defines strict geometric boundaries, the raster data model is used for continuous geographic features. This image is an example of raster data, where space is organized into a continuous pixel matrix. Each individual cell holds a specific measurement, like the temperature values driving these satellite cloud overlays across the continent. These models can be plotted on a flat geometry plane or wrapped around the Earth's spherical surface using the geography model and geodetic coordinates like latitude and longitude. Through vector and raster structures, the database now possesses a mathematically rigid language to describe physical reality. With the data structured, the system can build a working index. To solve the multi-dimensional indexing problem, spatial databases use a specialized structure called the R-tree. Instead of indexing individual coordinate points, the R-tree indexes spatial proximity groupings. Imagine a city map filled with our active rideshare drivers. The database groups nearby drivers together and draws a tight box around them, known as a minimum bounding rectangle, or MBR. The system is hierarchical. Those initial rectangles are grouped together and enclosed inside increasingly larger parent bounding boxes, continuing until the entire city is covered. Beneath the map interface, these nested rectangles form an inverted data tree. The database traverses these parent and child nodes to locate spatial boundaries. By indexing geometric boundaries instead of distinct points, the R-tree shifts the heavy computational burden from exact distance calculation to simple boundary intersection. We can see how this works in practice using PostGIS, the industry-standard spatial extension for PostgreSQL. This code block is the exact spatial query a back-end engineer writes to execute that 2-kilometer rideshare search. First, the stMakePoint function translates the passenger's raw latitude and longitude into a spatial geometry object. Next, the stDwithin function establishes the search area, drawing a precise 2,000-meter radius around the passenger. Now the rtree index takes over. The database checks the top-level parent rectangles and instantly rejects any box that does not physically intersect with the search radius. Rejecting just one parent rectangle eliminates the need to scan thousands of individual coordinates. It drops the O of n bottleneck in a single CPU cycle. The expensive mathematical distance equation is only executed on the handful of individual drivers located inside the final intersecting child rectangle. The rtree's boundary filtering is the reason a spatial query can process millions of active points and return the closest driver to your screen in milliseconds. This architecture scales far beyond consumer apps. Spatial databases are the foundational engines driving geographic information systems, or GIS. Instead of manually plotting zones on paper, urban engineers use GIS to query intersecting polygon models, designing public transit routes, and optimizing utility grids dynamically. Environmental scientists execute massive raster data queries over satellite imagery, comparing decades of data to track deforestation trends, map shrinking habitats, and monitor flood risk zones over time. For global supply chains, complex line strings are queried in real time to compute optimal delivery geometries for massive fleets of vehicles. GIS transforms static cartography into a dynamic mathematical model, capable of answering complex intersection and proximity questions at a global scale. Early data management was constrained entirely by the hardware and the linear structures available at the time. Standard ledgers and one-dimensional B-trees were built to sort strings and integers. They are structurally incapable of processing the dimensions of reality. True multidimensional computing requires specialized spatial data types to translate the physical world into code. It requires structural innovations like the minimum bounding rectangle to bypass computational bottlenecks and make geographic sorting possible. A spatial database is the mathematical engine that finally allows computer architecture to natively index, query, and understand the physical dimensions of our planet.